All right, let's get right into it. We hear this term pyrolysis oil all the time in the world of advanced recycling, right? And it sounds pretty straightforward. You take waste, you turn it into oil. Simple. But today, we're going to pull back the curtain and really look at the chemistry. And you're going to see why that simple name, well, it's actually a huge problem.
And hey, that's not just me saying that. This comes directly from the source material. You see, when a chemist or a refinery engineer hears the word oil, they think of something stable, something predictable, something you can put in a tank and forget about. Pyrolysis oil is none of those things, not even close. It's a completely different beast.
Okay, so if it's not really oil in the way we normally think about it, then what in the world are we actually dealing with here?
This right here is the key. You have to think of it as a reaction intermediate. Imagine it's like a cake that's only half-baked. All the ingredients are there, but they haven't settled down yet. It's unstable, it's super reactive, and it is still practically humming with the energy from the intense heat that created it. This is the polar opposite of fossil crude oil, which has had millions and millions of years to just chill out and stabilize underground. So to really get a handle on this, we've got to break down the different chemical personalities that are all hiding under this one very misleading name.
Now take a look at this table. What's wild is just how massive the differences are. This really shows what we're calling the quality gap. Look at the energy content. See how plastic and tire oil are kind of in the same ballpark as diesel? But then look at bio-oil. Whoa, it has less than half the energy. And then check out the oxygen content for bio-oil. It's just off the charts. And the pH? Bio-oil is screamingly acidic.
And this slide right here is the whole point of our deep dive today. We're not talking about one thing. We're talking about three totally different liquids made from three totally different materials, and each one brings its own unique, massive chemical headache to the table. So let's break them down one by one.
So first up, we've got bio-oil. This is the stuff that comes from biomass, like wood chips or agricultural waste. And its entire story can be summed up with one word: oxygen. It is absolutely loaded with it, and that one fact changes everything.
This chart just says it all, doesn't it? In a typical fuel, what you want are hydrocarbons. That's where the energy is. Well, in bio-oil, hydrocarbons are the smallest piece of the pie. The overwhelming majority is oxygen and water. The source material even calls it liquid smoke, and that's a pretty good description. It's really not a fuel in the traditional sense. So what's the big deal with all that oxygen? Well, it's what's known as the oxygen penalty, and it's a killer. First, it's just dead weight, ballast you have to ship around that gives you zero energy value. It's why the heating value is so low. Second, it makes the oil immiscible. That means you can't just mix it with regular diesel. It would separate out, just like oil and vinegar. And finally, it creates all these super reactive molecules, like aldehydes, that just make the whole thing unstable. And then there's this, a pH of 2 to 3. To put that in perspective, that is as acidic as vinegar or lemon juice. So think about what that means. You can't just store this stuff in a standard steel tank. It will literally eat right through the metal. You need to use expensive, corrosion-resistant stainless steel for every single pipe, valve, and tank that it touches. Okay, let's switch gears to plastic oil. Now, this one is chemically a lot closer to what we think of as crude oil. It's mostly hydrocarbons, but it has a totally different problem, and this one is very physical. It's incredibly waxy. A good quality fuel has a really tight, predictable boiling range. Plastic oil is the exact opposite. As you can see here, it's a total mishmash. It's got everything from light stuff like naphtha, which is kind of like gasoline, all the way up to these super heavy waxes that are basically solid at room temperature. It's literally like someone mixed gasoline, diesel fuel, and a bunch of melted candles all together in one barrel. And within that mix, there are two key types of molecules we need to know about. You've got paraffins, which are great. They're stable, they're saturated, they make for good fuel. But then you have olefins. You see that C double bond C? You can think of that double bond as a loaded spring. It makes the whole molecule twitchy, reactive, and really unstable, which is a massive problem for fuel quality. So, what does all that wax mean in the real world? It all comes down to something called the pour point. And what that means is your supposedly liquid fuel can turn into a solid block of wax if the temperature just drops a little bit. Imagine trying to run a business where your main product could solidify in a pipeline on a chilly day. It's a logistical nightmare.
And that brings us to our third and final personality, tire oil. And yep, it's different all over again. This one isn't about oxygen, it's not about wax. Its entire identity is defined by a special class of molecules called aromatics. Aromatics are these ring-shaped hydrocarbon molecules. Now, some of them are actually quite valuable chemicals, like toluene and xylene. But the mixture also contains some nasty stuff. Benzene, that's the B in BTX, is a known carcinogen. And so are many of these polycyclic aromatic hydrocarbons, or PAH. So right off the bat, you've got this weird mix of high-value product and hazardous waste that you have to deal with. Now, these aromatics have a really dramatic effect on how an engine runs. They give the oil a high octane rating, which is fantastic for a gasoline engine. It prevents knocking. But they have a very low cetane number, which is what you need for a diesel engine to ignite properly. So it's great for your car, but it would be an absolute disaster in a semi-truck. A complete mismatch. And maybe the most shocking problem is this one. Aromatics are incredibly powerful solvents. This quote says everything you need to know. If you were to put this stuff into a normal fuel system, it would literally dissolve the rubber seals, the gaskets, and the fuel lines from the inside out. We're talking catastrophic leaks and failures. Okay, so we've just met 3 very different oils with 3 very different challenges, right? We've got the oxygen problem, the wax problem, and the aromatics problem. But here's the kicker. There is one universal flaw, one critical problem that ties all of them together. They are all fundamentally unstable. And this is how it happens. It's a process called polymerization. Remember all those reactive molecules we talked about? The olefins in plastic oil, the aldehydes in bio-oil? Well, over time, especially if they're exposed to a little heat or air, they start to link up with each other. They form longer and longer chains, and your nice, free-flowing liquid starts turning into thick gums, then sticky sludge, and eventually it can even form solid. And look, this isn't just some interesting chemistry fact. It is a massive business problem. This quote is so important. Unlike crude oil, which can sit in a tank for years, pyrolysis oil has a shelf life. Sometimes it's less than 3 months. It means you can't build up a big inventory. It has to be processed almost immediately, which requires this incredibly complex and expensive just-in-time supply chain. So this is really the bottom line. Calling everything pyrolysis oil completely hides the molecular reality of what's going on. To turn any of these into a useful product, you need a totally different game plan. For bio-oil, you've got to wage war on oxygen. For plastic oil, you have to break apart those waxes. For tire oil, you have to tame the aromatics. There's absolutely no one-size-fits-all solution here. Being successful in this industry isn't just about building bigger reactors. It's about mastering this incredibly complex, feedstock-specific chemistry. And that leaves us with one final thing to think about. Now that you understand the true chemical challenge, what do you think this all means for the future of advanced recycling?